Have you ever wondered how a character in a video game gets so good at navigating a level? Or how a robot can learn a new task just by, trying stuff out? Well, a huge piece of that puzzle comes from this brilliant 1992 paper and a concept called Q-learning. So let's dive in and see how it taught machines to learn from their mistakes and ultimately how to win. Okay, to really get our heads around this, let's start with a simple problem. Picture a robot. It's just been dropped right into the middle of a maze. Its mission is to find some treasure, but here's the catch. It has no map, no guide, absolutely nothing. It is completely and totally lost. So that's the big question, right? How does this robot, with nothing but trial and error, figure out the absolute best path to the prize? This is the exact problem Q-learning was built to solve. And to get how it works, we just need to nail down a few key terms first. First up, we've got the agent. Now, this is our hero, the one who's doing all the learning and making all the decisions. The paper calls it a computational agent, but for us, it's our little robot, just trying to figure out its world. Next, we have the state. A state is really just a specific situation the agent is in. So for our robot in the maze, every single square it can stand on is a unique state. Simple enough, right? And from any state, our agent can take an action. These are just the moves available to it. For our robot, the actions are pretty basic. It can try to move up, down, left, or right. And finally, we get to the most important piece of the puzzle, the reward. Every time our robot takes an action, the world gives it a little piece of feedback. It might be a big positive number for finding the treasure, or maybe a small negative one for hitting a wall or just wasting time. This reward signal is the only thing the robot has to learn what works and what really, really doesn't. So we've got our agent, we've got states, actions, and rewards. How in the world does the agent put all that together to build a winning strategy? Well, it creates what I like to call the ultimate cheat sheet. Let's take a look. So here's the main idea. The robot needs to figure out how good it is to make a certain move from a certain square. And I don't just mean the immediate reward. I mean the long-term value, the potential for all the rewards it could get down the line. It needs a scoring system. And this is that system. It's called a Q table, and you can basically think of it as the robot's brain or memory. On one axis, you have every state it can be in, and on the other, every action it can take. And notice how everything starts at 0? That's because at the beginning, our robot is completely ignorant. It has no clue what's a good move or a bad one. Every single cell in this table holds something called a Q value, and this number is super important. It's not just about the next step, it's an estimate of the total future reward the robot will get if it takes a certain action from a certain state and then plays perfectly from that point on. It's a measure of the total long-term quality of a move. Okay, so we have this big table of zeros. How does the robot actually fill it up with useful numbers? Well, it does it the old-fashioned way, by exploring. By living and learning. The whole process follows this really simple repeating loop. First, the robot sees what state it's in. Second, it picks an action to take. Third, it actually does the action and the environment gives it a reward and shows it its new state. And fourth, and this is the magic part, it uses that experience to update its Q table. And this right here is the engine that drives all the learning. I know, this formula might look a little intense, but it's really just the specific recipe for that fourth step, for adjusting the Q value. It's how the agent turns raw experience into actual knowledge. Let's just break it down into plain English. All this formula is really saying is this: take the value you used to have for this move and just nudge it a little bit based on what you just learned. It's a small correction, a tiny update. It's learning one experience at a time. So with every single step the robot takes, it gets some feedback, and one of those zeros in its Q table gets updated with a new number. And over thousands, maybe millions of these tiny updates, that table slowly transforms from a blank slate into a perfect guide for how to act. Now, this all sounds really good in theory, right? But the true genius of this paper wasn't just coming up with the algorithm. It was proving mathematically that it's guaranteed to work. This is the really crucial question. How can we be so sure that after all this wandering around, the Q table will actually show the robot the optimal path and not just some pretty good path it found by chance? This is all about convergence. To prove this, the authors gave us this really clever analogy. They said, hey, the easiest way to think about this is to imagine it all as a kind of card game. So the logic kind of goes like this. Imagine every single thing the robot does, every state, action, and reward gets written down on a little card. Over time, this creates this massive deck of cards, like an action replay of its entire life. The proof shows that if you keep sampling from this deck and updating the Q values, they are mathematically guaranteed to eventually settle on the one true best value. It's a promise of perfection.
And that guarantee, that mathematical promise, is exactly what cemented Q-Learning's place in history and really helped shape the future of AI.
One of its most powerful ideas is that it's model-free. What that means is our robot never has to build a complete map of the maze inside its head. Instead of learning the rules of the world, it just learns the value of its actions directly from experience. This makes it way more flexible and a lot more efficient.
And that's really the heart of it. This paper gave the world a recipe that was simple enough to actually use, powerful enough to solve real problems, and, crucially, it came with that rock-solid mathematical guarantee that it would find the best solution. And hey, don't just take my word for it. As the authors themselves put it, that kind of guarantee had eluded most methods of reinforcement learning before this. It was a true game changer. Which brings us to a final thought. This idea, which started with a simple robot in a maze, is a direct ancestor to so much of the AI we see today. It really makes you wonder, when you have a tool that is guaranteed to find the best way to do something, what happens when you point it at problems like mastering complex strategy games, controlling sophisticated robots, or even navigating the chaos of the financial markets? The legacy of Q-Learning is absolutely everywhere.